last item in chapter 17. It is complexes which are still in equilibrium. We'll go through the definitions of them. We've done a little bit before. One of the biggest aspects of complexes is they deal with the definition of Lewis acids, which is electron pairs acceptors and donors. Remember, we did this where we said that a Lewis acid was an electron pair acceptor, and a base is an electron pair donor. In organic, they're going to refer to an acid as an electrophile, because remember, a file is a lover, like a bibliophile is a book lover. So a nucleophile wants a nucleus. So acids and bases, when they form a complex, this is a complex here. So this is your Lewis acid because it's missing a pair. This is your Lewis base because we have lots of pairs. And so we've seen this before when we did the Lewis acid bases. This is going to complex here to form this complex. Now, complexes are different because they tend to stay aqueous. They may look chunky, they may look gelatinous. It's very common for these to look gelatinous. So they fall into the solubility, but they're not forming a true precipitate solid. You can take a centrifuge and get them out, but it becomes an issue if you're doing particular labs. Now, again, predict which is a Lewis acid base pair. Again, I'm not going to ask you these. We've done these before. Remember, this has got a pair, so it's a base. This one's missing a pair, so it's an acid. This one's got two pairs, so it's a base. This one has no electron pairs, so it's an acid. And this one's just weird. Remember, that was our radical, which makes it an acid, but that's strange. This one's got a triple bond, so it's actually short electrons. So it wants electrons. That makes it an acid. Again, I'm not going to give you these individually. I will give them to you in an equation type of format, because let's take it farther from the Lewis acid base and talk about complex ion formation. Now, unlike KSPs, where you have a solubility product and you just produce a precipitate or not, complexes are a little wilder. They're a little wilder in terms of their values, but they're also a little wilder because for some bizarre reason they give the forming one value and then the dissolving the inverse of that. So let's talk about this. The formation constant is the product of the species both ions and complex that are in aqueous form. So again, unlike solutions, which are solids and drop out, complexes still say aqueous. The formation complex is another K, but it's K of formation. And remember, it's the product over the reactants. Now, we take it a step farther because formation is your KF. That's your complexes forming. If you go the other way, they call that a KD. And the KD is equal to 1 over the KF. So basically, they're inverses. And we're going to stick with pretty much with KFs, even if it's a KD, we're going to call it a complex. We'll just call it KF. But be aware that they are different. Again, we are limited as to what we can do, so I'm going to tell you that they're different. If you take an inorganic class later, then you may encounter them. Otherwise, we will just go through the basics. Now, here are your KF values. And what's interesting is first off, notice that they're positive, okay? And notice that some of them tend to be very large, okay? And remember, these are complexes, so they stay aqueous. So notice in your equilibrium, you're going to keep the product in your equilibrium, okay? So let me real quick go back to this one and say, let's do this first one. So your KF is going to be equal to your silver nitrate, amide. It's called, that's how you pronounce it, but ammonium. And on the bottom is your reactant, which is your silver ion, and your ammonia ion squared. So notice that you don't lose your product or your reactant, unlike with your KSPs. Okay? So that brings us to coordination compounds. Now, coordination compounds are when you take transition metals, and remember your transition metals are the D block, okay, iron, cobalt, etc. Okay, they're going to link with Lewis bases, and these could be neutral or charged. To form complexes. Okay? Now, because this is very common with transition metals, then you can call these complex ions or coordination complexes. Tomato, tomato, they're pretty much the same thing. And so basically they're Lewis acid base complexes. And they are formed around a central metal ion. Okay, so it's basically the product of a Lewis acid-base reaction. Okay, now these are interesting to look at. Some of them are really cool in terms of colors, etc. And that brings us to a couple other terminologies used associated with coordination complexes or compounds. And the first ones are ligands. Okay, these are molecules or ions that bind to the metals. Metal ions. Now, they're interesting because they're either called dentate or chelators. Okay, dentate means basically teeth. And so they tend to be mono, bi, tri, etc. And so these are usually individual species that when they form the complex, it's like they look like a bite going on. The other ones are chelators, which mean claws. And so the teeth kind of come in from the outside and kind of stick on, and there can be multi from the same one. But chelators are claws, so again, they can be mono, bi, tri, but they tend to wrap around. So think about taking a bite out of something versus picking it up. Okay? And the typical ligands tend to be monodentate, or you could have the bi, tri, tetra, and again, this applies to the chelators, etc. Now, we also call these coordination compounds or complexes. What's that mean? Well, the coordination number is actually important, but it's actually really simple. These are the number of ligands that can bind. Okay, so I'll show you an example here. So if we have a reaction where we have the Lewis acid with the Lewis base and we get the complex, notice that there are 6 surrounding. 1, 2, 3, 4, 5, 6. Now, in some coordination compounds, you have the same species, and other things you can have different molecules. So the number that pick on, that's your coordination number. And again, this can vary. 6 is usually the maximum, and that's very common, but you can have ones that are 1, 2, 3, or 4. If you look at your KF values, you will see this. Again, these are 6. One other thing is you have stereoisomers, which stereoisomers are different arrangements in space. And again, I'm not going to test you on this, but I'm going to go over it because you may see this later, and you'll definitely see cis and trans later when you get to organic. But basically, cis is on the same side, and trans is opposite side. So when we look at this, what we have is the chlorines are different. They're opposite. Whereas the chlorines are here, they're on the same side. And when I say same side, they're on a plane. Okay? And so these are ligands, and these are chelators. And so if you'll notice, you don't know what enantiomers are, but you can look at it, but they're cis and trans. This I took from this one. There's another one. These both have coordination numbers of 6. I accidentally deleted the one that didn't. But 5, 4, 3 are not uncommon. And again, cis, if they're on the same side. Trans is easier because in this case, look where the chlorines are. Here they're on the same side. Here they're on the same side. Here they're opposite of the molecule. Okay, and again, I'm not going to ask you about that. But what I will ask you is I may ask you to work a problem, and these are relatively easy, but sometimes they have a little bit of a catch. Okay, what's the concentration of the free silver present in a solution that initially contains this much silver cyanide and that much cyanide? So what you're doing is you're going to start with the silver ion, and you're looking at it, you're going to have the cyanide, and you're going to produce your complex, which is silver cyanide minus. Now, notice that a lot of these complexes will have charges, and that's okay. So what we want to do here is calculate it backwards. Okay. So if you'll notice that our KF value is the silver cyanide, squared minus divided by the silver ion and the cyanide ion. Okay? So what's going to happen here is that, I forgot to square it. This is 5.6 times 10 to the minus, positive 18. All right. So what's going to happen on this one, and I'll be honest, I'm looking at how I set it up, and I set it up backwards. So we're going to walk you through it. Now I'm going to take the time to work the problems as we go on this one. So because your KF value is positive and large, then you're going to assume all of the silver goes into the complex. So when we set up the ICE table for this one, we're going to start with all of the silver gone to the complex. Okay, that leaves us with a silver value of 0, and that's the one we're looking for. Now, because the cyanide concentration has to be equal to 2 times the silver concentration because of the stoichiometry, then the cyanide that's left is going to be equal to 1 minus 2 times 0.1, which is equal to 0.8 molar. That's how much free cyanide is left. So we have our value here for our cyanide. Now, we're going to solve for the silver, so we're going to have to gain over here, so we're going to gain 2x, and we're going to lose x. So at equilibrium is 0.1 minus x, 0.8 plus 2x, and x. Okay, so my KF is equal to what we have up here, so it's 0.1 minus x divided by x times 0.8 plus 2x squared is all equal to 5.6 times 10 to the 18th. Now, bottom line is this is huge and positive, so dissociation will be minimal. So we get 0.1 over x times 0.8 squared is equal to 5.6 times 10 to the 18th. Okay, so 0.8 squared. So this gives me 0.1 divided by 0.64x is equal to 5.6 times 10 to the 18th. 5.6 to the 18th. Whoops. So I end up with 0.1 is equal to 3.584 times 10 to the 18th x. So x is equal to 2.79018 times 10 to the minus 20th. So that means my silver concentration that's free is going to be equal to 2.790 times 10 to the minus 20th molar. Okay, that's not big at all, but we made the assumption, so we're going to check it. Now, you're like, wait, we made the assumption on two things, 0.1 and 0.8. Well, 0.8 is a whole lot larger than 0.1, so 0.1 is the one we're going to check. So check with the smallest amount, which is 0.1 in this case. So we take the 2.790 times 10 to the minus 20 divided by 0.1 times 100. Whoops, that looks really weird. 0.1 times 100. So divided by 0.1 times 100. This is going to be 2.790 times 10 to the minus 17th percent, which is much, much, much less than 5%, so we're valid. Now, you could have walked through that whole math thing. I did that on my paper. Let's just say it's ugly, we ended up with not a binomial but a trinomial, so you had to put x cubed into your calculator, and trust me, you get a comparable number, so it's not worth the effort. So we're going to work this one more time because you have to work it backwards. And I want you to see this one more time. Okay, so here we go. We have copper 2 plus 4 ammonias will produce the complex with 4 amides. Okay, we have a large positive value, which means all the copper will move to the complex. So, if we look at it, if all of our copper for ammonia goes to the complex, and I'm going to write this out as opposed to just verbally say it. So what happens is we're going to start with 0.1 and 1 and 0. So it's all going to go. So we're going to lose all of this, which means we're going to have to lose 4 times that, which is 0.4. And we're going to gain 0.1. So we're left with 0 here, 0.6, and 0.1. So when we come over here to do our ICE table, now everybody realizes that coefficient-wise, if it's 0.1 and it's 1 to 4, then you lost 0.4. So we'll set up our 0 here. We have 0.6, and this is 0.1. So it's going to shift. We're going to gain 4x here plus x. So it's x 0.6 plus 4x and 0.1 minus x. This again is our Kf, which is equal to our complex for 2 plus divided by my copper divided by my ammonia to the 4th is equal to 2.1 times 10 to the 13th. Okay, we're going to assume that the dissociation is minimal because Kf is large and positive. So, I forgot to write this in. This would have been 0.1 minus x. This would have been x, and this would have been 0.6 plus 4x raised to the 4th power. So then that gives us 0.1 over x times 0.6 to the 4th is equal to 2.1 times 10 to the 13th. Okay? So when we do the math, we're going to get 0.1 divided by 0.1296x is equal to 2.1 times 10 to the 13th. So 0.1 is equal to 2.7216 times 10 to the 12th x. If we solve for it, x comes out equal to 3.6743 times 10 to the minus 14th, which would be the copper ion concentration. But we got to check it. So again, we're going to use the smallest amount you subtracted from, which was the 0.1. So it's going to be 3.6743 times 10 to the minus 14th divided by 0.1 times 100 which gives you 3.674 times 10 to the minus 13th percent, which is less than by a ton, 5%, so it's valid. Now, in the cases of complexes, complexes are really interesting because they're always going to form. So your assumptions are going to be valid 99% of the time, assuming it's positive, which it should be, and it's large. We saw what it did for 13, 8, etc. So you should be good on that one. All right. This is associated with the lead batteries and contamination. This has to do with the Flint Energy contamination of lead in the drinking water in Flint, Michigan. And it's actually worth reading because, of course, in the news they don't go through this, but the contamination was really due to the breakdown of complexes and precipitates on the sides of the plumbing by changing the pH. So it's kind of interesting and it's timely, so I would read that one. Okay, and then the next one you really need to look over because I know there will be a couple questions from it on the test.